In this video, we will model the roll of a fair die, six-sided die. We'll begin as we did before with a random number generator from 0 to 1. But since a die has 6 sides, we're going to multiply by 6. And since a die has integers on each side, we don't want to deal with those decimals, so we need to round. But if I hit F9 and see what some of the values I'm going to get here, sometimes I'm going to get a very low value that's below 0.5. If I round that 0.39, it's going to round down to 0, and a die doesn't have a side with 0 on it. But fortunately, Excel has a function called round up. So if I round that up to a whole number with 0 digits, then I can hit F9 and kind of see what I'm going to get there. And I could do this forever and realize that I'm only going to get a 1, 2, 3, 4, 5, or 6. So we have the formula that we're looking for. Similar, let me show you what those were. Similar to last time, we can go ahead and nest that into one formula. Now when I recalculate, those two die don't always roll the same answer, because this one is getting a random number from inside the cell. This one's getting a random number from up here in B11. Nonetheless, we've come up with one formula to give us the model of the roll of a fair die. So let's get rid of this stuff and let's do a simulation. Let's do 250 rolls of the die and see what we come up with. What we would expect is that for each possible outcome, the frequency would be about 17%. Let's see what we really get. Okay, I went ahead and built that for 500 realizations. And so for each one, we will calculate an outcome from this cell and put it in column J. Let's go ahead and color these to remind ourselves that this is the cell that holds the outcome we want to record in column J, and that these are the cells that will be plugged into an arbitrary spreadsheet cell somewhere. We're going to use this one because it's not used for anything else. So when we create our data table and it asks where we'd like to plug each of these values in the column, we'll tell it just plug them right there because that won't hurt anything. And it really doesn't matter. We just want to use this data table to recalculate the spreadsheet so we can get a new roll of the die. Now there are two ways that we can look at the outcomes that we got. We can use a COUNTIF, or we can use the frequency. And then in both cases, we're going to count the number of sixes we got, for example, divide by the total number of outcomes to find out the percentage of time we got a 6. The way COUNTIF works is we give it a range to count, but we say only count if the numbers in that range are equal to this criteria, like so. Now we want to be able to copy that down 5 more times, so we'll hit F4, get our absolute references, and we find out we got 94 ones and 72 sixes and so on. If we want to convert that to a percent, we can come back and divide by just the simple count of that range. Control Shift down, F4, and then we can copy that down. Come over here and copy and paste special formats. While we're at it, we'll paste special formats there as well. Now how we use the frequency, and if you'd like to look into this, just do some help, Google some help on frequency. Frequency requires that we highlight all the range we want the output to be in. We type frequency, grab our data array, all 500 outputs, and then tell it which bins we want it to bin those outputs into. Now frequency is super nice if we have decimals in our data over here. The way we just had discrete outcomes 1, 2, 3, 4, 5, or 6, we were fine getting by with COUNTIF. But if we had a 1.3 or a 1.47568 in here, COUNTIF would not have been able to count that. and the next best way to do it would have been frequency. So going forward, we're going to use frequency. We'll do Control-Shift-Enter. And we didn't divide by the count, so let's go back and do that. Same way we did with COUNTIF. Control-Shift-Enter. Yes, go ahead and close that parenthesis out for us. And you see we get exactly the same answer using the frequency function as we do the COUNTIF function. So take a look at those, but we'll be doing this going forward. Now let's compare this on a chart. Let's build a chart of what we got and what we expected. Starting with what we expected, let's add what we got with Control-C, base special, series name in the first row, new series, values in columns. And this doesn't look too good because it's scaled from 15% to 18%. Let's go ahead and scale that better. Scale it from 0 to 50%. And now every time we hit F9 to rerun the simulation, we find out that 500 iterations is getting us a pretty good representation. This one doesn't look great. We're up to about 20% 5s and only about 15% 4s. But probably 500 for one die is going to be reasonably close. If we were very serious about making a purchase based on our outcome, we might go ahead and run 1,000 or 10,000 iterations. Take a little bit more time, give us a much more accurate number. Finally, I think we should add some labels to the chart. Now let's move on to simulate 2 dice. We'll use the same formula that we generated for 1 die. Enter that in for our first die and enter it in again for our second die. And again, since we're using different random number generators for each of these dice, we can expect a different number. If we had put rand in a cell somewhere, referred both of these to that cell, then of course we'd get the same answer on each die, not what we want. So to add those together, we'll just hit Alt equals for a sum. That'll be our output. And let's think about what we might expect as results here. We could get on either die a 1 or 2, 3, 4, 5, or 6. And so if we made a table of all the possible outcomes, we could have this die block the column plus this die block the row. What you see is there are a lot of ways we could get a 7. Only one way we can get a 2, or one way we could get a 12, and so on. So we're going to generate a triangular distribution out of this. Let's see if our simulation can match that. So our simulation over here, let's go ahead and do 500 iterations like last time. And not only will we capture the result, but let's capture the individual die 1 and die 2, because sometimes it's nice to have some intermediate results in there. So die 1 we're going to refer to right here. Die 2 we'll refer to right here. And the sum we could add right here, or we could just come in here and grab it from our model. Probably better practice. And since those are our output cells, we'll color them yellow. Color our input cells blue. And now we're ready to run the simulation. So we'll create the data table. And as we know, wherever we put these individual numbers doesn't matter as long as they don't mess anything up. We just want to use this to recalculate the spreadsheet 500 times. and put the results in the rows. Okay, so now we have 500 results. Let's use that frequency again. Let me get rid of this example table over here. And we know we can get a 1 through a 12. We'll call that our outcome. And probability. And had I captured the probabilities from that chart, they would have been as follows. Can't get a 1, so I'll delete that row. You'll want to go back and look at that chart and count up all the different ways you can get a 7. You'll find there were 6 ways. It went up diagonally. So we need to divide all of these by the total number of outcomes, which was 36. So we'll do a copy, paste, special divide, change that to a %. And these are the expected probabilities of rolling 2 die and adding the results together. Let's see what we really got. Let's use that frequency approach. Remember, the quirky thing about frequency is we have to highlight all of the cells where we want this array of results to go before we type frequency. Then we grab the data array, and it's just the sum that we care about. And then we will grab the bins array, close it out, and hit Control-Shift-Enter. Very important to hit Control-Shift-Enter. Would have been important to divide that by a count as well, but I can come back and do that. Control-Shift-Enter. Let's change those to a %. And you can tell we got pretty close to what we expected, but not exact. So let's do the same thing as before. Draw a chart comparing these two. And you can see as I hit F9 and rerun the simulation that most of these simulations do a pretty good job of approximating that expected triangular distribution that we see in the blue. So now that we've got some confidence in simulating the sum of some dice, let's go ahead and start to test some well-known statistical properties. For example, adding together, let's say, 10 dice, and see if we can approximate a normal distribution. Let's start about where we did last time with our 2 dice. Make room for 10 dice. So I'm just actually going to copy that down until we have 10 dice. Add them up. And now we have the sum of 10 dice. So let's build a Monte Carlo simulator to do 500 realizations. And let's simulate. We now have 500 possibilities of what we might get from rolling 10 dice. Let's do a quality check on that. Our maximum should certainly not be any more than 60. And that would be if every single die came up 6, which is probably pretty unlikely. We could calculate that. Sum that, and it looks like the max is about 50. That sounds reasonable. The minimum's about 19. That sounds reasonable. Don't see any outliers there. So let's go ahead and build a frequency chart. We'll start this showing outcomes from, we know we can't have less than 10. We know we can't have more than 60. Let's go ahead and build our chart accordingly. We'll use the frequency again. Need to highlight all the cells we want that to go into and type frequency. Of the outputs, I think we call that the data array, comma. And then we'll highlight the bins. the frequency, and this time I will divide by the count. Forgot to do that the last two times. And take the normal count of that and do a Control-Shift-Enter. And we should have a histogram showing the percentage of time that any of these outcomes happened. So if we convert that to a percent, highlight those two, I'm going to start with 1. We'll draw a chart. And that's that bell shape we were hoping for. Statistics class taught us that if we add together a large number of independent items, we should get a normally shaped distribution. And let me go ahead and add the outcomes to this. This is the easiest way I know to add x values to a chart. And so it looks like the mode is right around 34, as is the median and probably the mean. So we've now simulated 10 dice. We will move on to some applications for our class.